Welcome to this SciCon machine learning tool tutorial. In this video, we're going to be covering linear discriminant analysis, or LDA. So LDA is a classification technique, so let's briefly cover what that is. Classification is a machine learning technique that sorts data into categories, and it allows the algorithm to make predictions based on new input features. So linear discriminant analysis, or LDA, is used for classification by converting higher dimensional data into lower dimensional data. LDA attempts to reduce within-class variance and increase between-class separation amongst multiple classes with multiple features. This form of classification uses continuous independent variables and a categorical dependent variable, otherwise known as a class label. LDA uses the Bayes theorem to predict which output class a particular input data point will fall into. The Bayes theorem calculates the conditional probability of event A after event B has already happened using this equation, where this is the probability of event A when event B happens. This is the probability of event B when A happens. This is the probability of event A, and this is the probability of event B. Sometimes LDA has to carry out dimensionality reduction, which is where data that has two or more dimensions is projected into one dimension so it can be more easily classified. This allows the LDA to be used for classification of data with more than two classes. So this figure here shows that data is projected onto a new axis for simplified classification. So there are a few assumptions of LDA. The first being that the data within each class has to have a normal or Gaussian distribution, otherwise known as a bell curve, and shown in this figure here. All classes have to have the same covariance matrix structure. So the covariance is the joint variability of two random variables, and covariance is present if two elements vary together. Having a similar covariance matrix structure means that there's the same number of rows and columns within the matrix. And finally, data classes must be able to be separated by a straight line or plane. Advantages of LDA include that it is simple and not computationally intensive. It works well with datasets where feature number is larger than the number of training samples. And it handles situations where dependent variables are linearly dependent, otherwise known as multi-collinearity. Limitations of LDA include the fact that it must meet the previously stated assumptions, so the Gaussian distribution, the same covariance structure, and the data must be linearly separable. And LDA doesn't always work well in high-dimensional feature spaces. So our experimental data today is phytomining data. Phytomining being the cultivation of special plant species with the goal of harvesting them to obtain metals from soil. Input features for phytomining may include the species and variety of a plant, the tissue type, like the roots versus the shoots, treatments, and soil metal concentration. Output data may include metals present in the plant tissue metal concentration, new soil metal concentration, and biomass yield. So this is the SciCon machine learning program. I've started out with giving my project a name and a short description. I've already uploaded my grassdata.csv file, and for data type, I'm going to select tabular. You can see my data in this table here. For my target label, I'm going to choose species. There's two different species within this data set. For method, I'm going to choose machine learning algorithm. And for my algorithm, I'm going to choose linear discriminant analysis. And then for my evaluation metrics, I'm going to pick confusion matrix and click perform. So these are some results we might expect to see from this analysis. So this left figure here shows a really basic confusion matrix, and this is just a visual representation that shows if the model correctly predicted an actual data point or not. So the top shows the actual occurrence of the data. So it shows if the data is actually positive or actually negative or falling into either group 1 or group 2. And then the side shows what the model predicts. So either a positive or negative or again a group 1 or 2. If the prediction lines up with what the data point actually is, that yields a true positive. If it predicts a negative, but the actual is positive, that would be a false negative. If it predicts a positive while the actual data is negative, that would be a false positive. And if the actual data is negative and the algorithm predicts a negative, that results in a true negative. So this figure on the right here is a representation of what you might see from a confusion matrix, showing that 4 data points were correctly sorted into group 0. 1 data point was incorrectly sorted into group 1 when it was actually 0. 2 data points were incorrectly predicted as group 0 when they are actually group 1. And 3 data points were correctly predicted to be in group 1 when they were actually in group 1. So this table here shows something very similar, where most of the data points are correctly sorted into their actual class, but there are a few data points that were sorted into the false negative or false positive groups. This has been the Scikon machine learning tutorial for linear discriminant analysis. Thank you for watching.